Okay, hello everyone. Welcome back here. So now let's talk about more about weak bases. So usually a weak base, typically they're amines, but they also could be conjugate bases or the anions that are derived from weak acids. They're also weak bases. For example, sodium sulfide. Okay, so if we look here, so here are some typical bronze acids and their conjugate bases. So we see here water, conjugate base is hydroxide, and then, but the only exception, I guess, to that rule I just mentioned is hydroxide. Hydroxide is pretty strong base. But we have HCl, we have ammonia from ammonium, that's a weak base. Hydrogen sulfate, going to sulfate. Sulfate would be a weak base because the HSO4 minus is a weak base, a weak acid, sorry. And then you see here all the bases that form from the weak acids in this chart, in this table here. They will have the negative ions they formed will be also weak bases. So hydrogen dihydrogen phosphate, fluoride ion, citrate, acetate, hydrogen sulfate, bicarbonate, and those would be very weak acids. And this last one, borate, that's boric acid. So borate will also be a very weak base. And then water, in this case, hydroxide is not a weak base, as we had demonstrated up above, but that's the one exception. Okay. And then these Ka values, do not worry about that. What these values represent is the higher the number, the stronger the acids. So you see the strong acids, they have really large Ka values, much greater than 1. So they are considered strong acids, whereas weak acids, they're much less than 1. So they are considered weak acids because they don't dissociate completely. So that's why their values for dissociation are much lower. Okay, so what does water do in our reaction? Well, water is usually the solvent, but acid-base reactions, they can happen in the gas phase. If you take this picture on the left, we have HCl gas and NH3 gas. They collect, we open the bottles, they collect, and they form this white mist. They form a cloud of this white solid, and that's ammonium chloride. So it does happen in the gas phase as well, but we usually don't do reactions in the gas phase because they're very difficult to control. So we usually do them in solution. I don't know, to be honest, doing things in the gas phase, it would seem kind of boring in my opinion because you can't work with the glassware and things will just happen, I think, too fast. And I think it'll be hard to kind of collect the compound based on it's not being contained in the container. So, but gas phase chemistry does occur. But we typically don't do that. Okay. So in acid-base reactions, water can be seen as both an acid and a base, right? We've seen it go to hydronium ion, and we also seen it go into hydroxide. So, so in this case, we say water is amphoteric. So it can actually act as an acid or a base. So here's an example. Here's a hydrogen ion being donated to water. So it gains the water from an acid. They become H3O+, so it's acting as a base. Now the hydrogen, it's losing its hydrogen to a base. So now it's acting as an acid in the second example here. Ammonia is going to pick up that hydrogen from the water, hydrogen ion, and become ammonium and water again. And then if we combine both sides of the equations, we can cancel out hydronium ion and water on both sides of the equation. So it's kind of like an intermediary between a different acid-base reaction. So it can help, transfer the proton to another molecule. So in organic chemistry, we oftentimes say, okay, there's the acid-base reaction step. have water or another solvent like water do the deprotonation and protonation of the hydrogen to another molecule. So water in this case tends to end as a intermediary or pretty much a proton ion shuttle between between molecules. So water, even though it's a solvent, it does play an important role in the reaction. Okay. So does water form ions, and to what extent does water form ions? So water does form ions, but as you may notice, if you drink water, right, it doesn't taste particularly sour or bitter. So so water doesn't have any acidic or basic character by itself. It usually has to have help from another compound. So it does dissociate in solution, but if you look at this picture here, it's rather small. So think about this picture as a screenshot of, say, water and its molecules in action here. So one has dissociated to ions, right? So if you think about this, a big picture of like the bulk, a small picture of like a huge sample of water, you could think of it as like saying, okay, here's 20 water molecules. Now, this is going to be a relative percent of how much water is ionized. So if you think about it, so the water is so neutral that it does not form these ions normally. So that's why we don't ever write water as H3O plus and OH minus, because the extent to which they exist in this form is very, 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 very small. So to give you an idea of how little the ions form in water, we could say this. We would have to look at an average of 25 million snapshots before we encountered another pair of these ions. So there's no way water is acidic or basic. Now, there's like high pH water, and that's because it's not pure water. They add this up to the solution to make it high pH. And it's probably like a small portion of the water anyway, so they just claim that, okay, high pH, alkaline pH, alkaline water, it could boost, give you the electrolytes you need, that sort of stuff. I don't buy into that. I like my pure water with like some minerals to get to, keep me balanced. But water, pretty much neutral. If it was any near acidic or basic, the flavor would definitely be affected. Okay, so we can actually calculate the concentration of water. So at 25 degrees, the density of water is approximately 0.9971 grams per centimeter. Oh, like what we did in the first slide, we determined the density of water. So therefore, if we use this value, we can calculate the molarity of water for any sample of water. So any sample of water will be 55.35 mole H2O per liter, or 55.4 molar approximately. Okay, so that means the concentration of the hydroxide and H plus ions are very small, so it makes water safe to drink. Okay, so in this case, we could say water has the ability to auto ionize itself. So one more molecule will accept a hydrogen ion for a hydrogen atom from another molecule, and that will form both H3O plus and OH minus. So we say the concentration of H plus or hydronium and hydroxide are approximately the same in water, okay, in neutral water. So in this case, we say, okay, the relative concentration is approximately 1 times 10 to the negative 7 molar. So that's really small. Okay. Now, if we compare the ratio here, the ratio is really small. It's It's not even a percent. It's like 0.0000%. It's a very small percentage, so it's not a lot of it is going to be ionized. So that's what makes water safe to drink. Okay. Okay. So to kind of do these so this is what we call pH calculations. We're going to talk about pH calculations. We can calculate the amount of hydronium ion and hydroxide ion by using what we call a water dissociation constant, or Kw. Okay, so Kw is this ionization constant for water. So if we plug in this equation here, Kw equals the concentration of H plus times the concentration of OH minus, we can say, okay, they're approximately the same, 1 times 10 to the negative 7th, 1 times 10 to the negative 7th, and usually we don't include units when we're calculating a constant like this, so I omitted them. So it's going to be 1.0 times 10 to the negative 14th at 25 degrees Celsius. So that's a very weak acid. Several orders of magnitude weaker than the acids in this list, in the weak acids list here. See, several orders of magnitude weaker. So water is right there. So it's not exactly the Ka for water. That's calculated a little bit differently, but it's you see there the ability to become ions is a little bit is very small. So it's around that range, 1.4 times 10 to the negative 14th. Okay, so it's very small. Okay. So if we have this information, we have Kw, and we know the concentration of either hydronium ion or hydroxide ion, we can calculate the other, and we can also calculate a value of the concentration. Well, it's a measure of the concentration. A value of the concentration is just the concentration itself, but we can put the we can classify the acidity of a solution based on a number scale, and that's called pH, or as the measure of how acidic a solution is. Okay, so pH as a measure of ion concentration for H3O+. So pH will always be the measure of the H plus ion in solution. So it gives us a number scale that's easier to work with than all these small numbers with scientific notation. So we say the pH is the negative log of H3O+ concentration, so H plus concentration. Okay, and the POH is the opposite, is the measure of the concentration of OH minus. So the higher the OH minus, the more basic or the higher the pH will be, and then the more acidic something is, the lower the pH will be. But I'll go into that a little bit more when we do these calculations. Okay. So let's do an example. Using this equation, let's calculate the pH of Pepsi Cola. If the concentration of the ion of H3O plus is 0.0035 molar. Okay. Okay, so we're going to set up our equation here. We're going to say pH equals negative log H3O plus. So the brackets just mean concentration. So you're going to put a unit of molarity for concentration. So in this case, we have, and it's usually, the concentration is usually in molarity. So we're going to say negative log 0.0035 molar. Okay, so when we do that, we will get out a number, a whole number, and in this case, we're going to say it's 2.46 as our pH. Okay, so no units, just a number. So sig figs. So if there's 2 sig figs in our concentration, there should be the same number of sig figs, or same number of sig figs in what we call mantissa. So the mantissa is the numbers after the decimal. So the base of the pH is the first number, and then the mantissa is the what's after the decimal. So we must have. So here is 2 sig figs. 2 sig figs. So we must have 2 sig figs. 2 sig figs after the decimal, okay? So when we're doing these dilute calculations, make sure you have the correct number of sig figs. Don't keep all the numbers. We can't report our values past the accuracy of the least accurate measurement. And in this case, it's the concentration. Okay, so 2 figs after the decimal. All right. Okay, so let's move on here. Okay. So these equations, we can only use these equations for very dilute solutions. So we cannot use these equations. So we cannot actually calculate the pH for solutions we make in lab because it won't be accurate. So that's why like for these kind of questions, we could use these equations as an approximate value. So, but they won't be exactly the pH that we would measure in the lab. So only for very dilute solutions. And the reason for that is because we're making some approximations in the equation for pH. And that's based on the fact that for very dilute solutions, the pH or the hydrogen ion in solution, it approaches this value that is constant. And when you get more concentrated solutions, that thing we measure is no longer very constant, and it's very dependent on the ions in solution. But that's all I'll talk about that. We don't need to know that right now. So just know that these equations are only for very dilute solutions, and we can only approximate the pH or pOH for real solutions. So in chemistry, there's often a disconnect because what you actually learn how to do these calculations, and in fact, they're just mere approximations. We try to get to the accurate value, but in calculations, there's always going to be some source of error because the calculation doesn't take into account some parameter or something. So in this case, I want to make it very clear that these cannot be used and like when we do lab reports, we can't use the negative log to figure out the pH. We'll have to use a pH meter. So we'll never use these in like a lab setting. Okay? So the use of a pH meter, however, is how we measure the pH accurately in lab. So that is that will record the electrical activity of the hydrogen ion in solution, and that will generate a signal that's accurate in the pH meter. So these pH meters are calibrated very accurately. So that's how we record pH in the lab. We never use like let's just use our calculators. We actually get it from an instrument, just like mass or volume, using our beakers or balance. Okay. So if we know the pH, then we can determine the hydrogen ion concentration. So that's the thing we usually calculate from the lab, the concentration based on the pH value we recorded. So if we know the pH and we want to know the pOH, we can use this equation, which is derived by taking the negative log of our Kw expression. So here's our equation that we're looking at, that pH plus pOH equals 14. So if we take the negative log, because if you look right here, the log of a number, usually the log of a number that's less than 0, or sorry, less than 1, it'll be negative. And then log 1 is 0. Then the log of anything greater than 0 is positive. So to keep numbers, since we all usually the solutions we work with are pretty much in the range of 0.01 to like 0.1 or like 6 molar, or something like that, we use the negative log to make to ensure that our pH values are positive, or usually positive. So we're not working with negative numbers, because thinking about a less negative or more negative number, it kind of messes with our brains. So it's much easier to connect. Okay, this number is lower than this number if they're both positive values. Okay, so we take the negative log on both sides. And we just treat Kw as a concentration. Remember, we took the negative log with H3O plus, that became pH. So we're gonna now. Oh, sorry. This should actually be Kw. Sorry, that was a typo. That turns into pKw. So sorry about that. So it'll be negative log H3O plus negative log OH minus equals 1.0 times 10 to the negative 14th. So remember, when we do logarithms of a product, we can rearrange it into addition. So we can say, okay, log H3O plus, negative log H3O plus times OH minus is the same thing as writing negative log H3O plus the negative log of OH minus. So we can rearrange it like that. And then the logs will turn our variables here into p values. So pKw equals pH plus POH, which equals 14. Because if we log, so we should probably say this as well. And then we negative log this as well. So that will turn that into 14. And then we can simplify this to say pH plus POH equals 14. Okay, so if we know the pH and POH, if we know the pH value and we want to find the POH value, we can use substitution here to solve for POH. Okay. All right, so I'll end things there, and then in the next video, we'll do an exercise of calculating the H3O concentrations, OH concentrations, and then the POH as well, and then we'll discuss more about the pH scale and what do these numbers mean. So I'll see everyone in the next video. All right, take care.